Okay, good morning. So let us start the lesson. So as you know that we are trying to prepare ourselves for mathematics Olympiad competition, and then we are actually doing planar geometry here. And if you remember, planar geometry is a type of geometry that you are dealing with shapes and figures that can be embedded in a two-dimensional plane, yes? So you shouldn't expect objects like pyramids or cylinders or cubes that are dealt with in another branch of geometry, which is called solid geometry. And we don't have any kind of questions regarding solid geometry in the mathematics Olympiad questions. So this is why we want to start learning about planar geometry. So let me just have a crash review and completion here. So we talked about angles, yes. So this point is called, for example, the vertex of the angle, and then each one of these are called side, or sometimes people call it arms. And then if you want to name it, you can just simply name it like that, or you can also name it, for example, by putting labels on the arms and then call it angle OAB or angle BOA. Of course, we already know about these things, so I don't want to review these very simple things. But one axiom that we learned, we had two axioms, yes? One axiom was the parallel axiom, that it is claiming that if you are working on a plane and you have a straight line, L, and then you have a point A outside that does not lie on the line, then you can draw a line parallel to L passing through A. This is one part of the axiom. Another part of the axiom is the uniqueness part. So it means that you can do it, but you can do it in only one way. So it means that I can draw a line parallel to this, and this line is unique. So L prime, and we say that L prime is parallel to L. By the way, another way to look at these objects, we consider L a set of points in the plane. So we usually use the symbols and notations from set theory. But of course you will study a little bit of that in Math 5. But I want to use this, I have already introduced you. For example, if I want to say that point A lies on L prime, I consider A as an object or as an element of the set of points which actually constitute L prime. And I would write A belongs to L prime. So this notation is very common. So this, in geometry, we can say that this object belongs to this set, but I am assuming that L prime is a set of points and this is one of them. So in geometry, we can read this that A is on the line L prime. Okay, we had also another axiom. Do you remember what was that? If we have two lines that are parallel, which is possible if we accept this axiom, and I told you that what the meaning of axiom is a statement regarding the primitive notions that in that setup, but we don't prove it. We cannot prove them. And then we want to have the number of axioms as low as possible. Yes? Okay, so if I have two lines, L and L prime, parallel, so let me write them L1 and L2, it's better. L1 and L2 are parallel. If a third line comes and cut these two lines, this is called a transversal. Yes? And then I hope that you remember, I told you that if you have a line that cuts one of these lines, it definitely will go and cut the other one as well. Why was that? Do you remember? Let us recall a little bit. Yes?
Well, you said last time that we should consider it an axiom, right?
No. This is not an axiom.
Well,
No, axiom, the axiom will come here. But this is an axiom. My claim is this. I want you to review a little bit of things. I am telling you, if L1 and L2 are parallel, and a third line, call it L, cuts the first one, will definitely go and cut the other one.
Sorry, I mixed them up.
This is not axiom.
Yes, sorry.
Okay, but this can be concluded from this parallel axiom. Why is that? Because if this line does not cut L2, it means that N, L, and 2 have to be parallel. And then if I consider this intersection point, the point A, L1 is already parallel to L2 according to my assumption. If L does not cut L2, it means that L is also parallel to L2. Then it means that from this point, which does not lie on L2, I have two lines parallel to the same line, which is in contradiction with the uniqueness part of the parallel axiom. Yes? So that is one thing. And then this one is axiom. This angle, if I call it alpha, and this angle, they are called corresponding angles. Yes? This we assume that they are equal. Of course, this is not completely counterintuitive, it's very intuitive, but I just want you to understand, no, we accept this as an axiom, and then we follow other things coming from these two axioms. I have seen books that they have accepted other axioms, and then they are able to get this as a theorem. But let us make things simple. I think let us take this as an axiom. Many standard geometry books are taking this as an axiom. So alpha is equal to beta. But of course, alpha is always equal to this angle, if I call it, for example, theta, yes? But this is not an axiom. We are able to prove that alpha and theta are the same. What was the name of these two angles? Do you remember? There are two names that I have seen in literature. Either they use it opposite angles, or another very strange angle. I don't know what is the source of that. Sometimes they call it vertical, a pair of vertical angles. I really don't exactly know why this is the case. But anyway, alpha and theta are the same, not because of any axiom. Do you remember why alpha and theta are the same? Yes, because we can consider, for example, this angle. Let me call it lambda. Then alpha plus lambda, alpha plus lambda is this straight angle, which is 180. And for the same reason, theta plus lambda is also 180. But lambda is common in these two sums. If you just move it around, then alpha and theta are the same. So they are simple things. And then, of course, I will have another, and then I have, for example, let me use xi. Yes, that is also a Greek letter. Yes, so this is called xi. And then, I don't know, I have other here, rho, and I have sigma and mu, for example. So, if you see, when I have two lines and one transversal line, I have 8 angles involved. In most cases, 4 of them are acute angles. So, that this acute angle is equal to that acute angle is not an axiom. This one is equal to this one. But why theta is equal to beta is somehow related to my axiom, because theta is equal to alpha, alpha is equal to beta, so theta and beta are also equal. And then all the other angles that you see, so the blue, so alpha, beta, alpha, theta, beta, and rho are all equal. Lambda, xi, mu, and sigma are all equal. These are obtuse angles. The angles greater than 90, less than 180 are called obtuse angles. And the angles between 0 and 90 are called acute angles. So I need only one axiom. If I accept that alpha is equal to beta, then I can conclude that all of these angles, exactly according to what I explained, are equal pairwise. Yes, is that clear? But what is the connection between this xi and beta? That's also good, because you are going to solve problems. It is very good to have some kind of, how do you say it in English, prototype example or whatever in your head, so that you can immediately compare things. And then, I mean that they are very, very simple, but if the problem itself is a little bit complicated, it's better to have these patterns in your head so that you can immediately adjust the hard problem, the pieces of the hard problem with the patterns that you have, and then try to extract the information out of it, yes? So here, What is the connection between these two?
They're complementary.
No, that's called supplementary. So that's also good that you mentioned that. So supplementary, we say that x and y supplementary means x and, so let me just forget about this. X plus y is 180. Yes? And then we call them, x and y are called complementary if x plus y is equal to 90 degrees. Yes? And of course, I would call x the supplement of y and the other way around, and I call x the complement of y and the other way around. So this is clear. This angle and that angle are supplementary. Yes? Okay, there is a special case that if I have two lines, and then I will draw that line perpendicular to that. So I have L1 and L2 parallel, and then this transversal is cutting the first one with angle 90 degrees. Okay, can I claim that this will go and cut the second one at also 90 degrees?
Yes.
Why is that? Is it an axiom or not?
It's an axiom.
It's like this, the axiom of corresponding angles, yes? Because when I see that this angle is 90, I am looking for this angle, but this angle and that angle are corresponding angles, so that is also 90. So we can see that if I have two parallel lines, and if a line cuts one of them at right angle, it will definitely cut the other one at right angle, yes? So that is also just another way, another version or another special case of this corresponding angle theory. Okay, so if I want to ask you something about what is the main, do you remember? What is the main consequence? I mean, I don't know if the main word is correct, but that is very fundamental to our geometry, Euclidean geometry. What was the fundamental consequence of this axiom? I'm intentionally asking questions in this way because I want to warm up a little bit. So, probably the easiest theorem that comes immediately out of it.
Triangle.
It's about triangles, yes? So that's immediate consequence of that one. So what does it mean? But by the way, let me tell you, just refresh your memory. For that theorem, that is the theorem. I want to prove that the sum of all interior angles of a triangle is 180. Every probably even primary school student knows about it. But the point is that how many axioms do I need to prove that? I want to prove it again, so let me just tell you first. I have this triangle. By the way, the point is that all my proof should be independent of the way that I illuminate the triangle in front of you, because I want to prove it for every triangle. Of course, in geometry, I draw a picture, but I have to be careful. Every sentence that I write as a proof will be exactly without any change, without any changes, if I change the triangle to any other triangle. So that is really fundamental if you want to be careful about logical point. So the point is that I want to prove that the angle A plus angle B plus angle C, these are called interior angles of my triangle. It's 180 degrees. Not just for this triangle, for any triangle that you can draw. Okay. Yes. So how should I prove that? Yes. Do you want to say something? Yes.
What do you call it? You extend the line BC.
Okay, we can, if you want to. I don't know. Do you remember? I do not. So there is another name which was new to me as well. We produce BDC. I really don't understand that. I prefer to use the words that I really understand. So I would say extend. Yes. So yes, you say that you extend. This is a line segment, but this line segment is part of a bigger portion. It's the line, and then But this I don't need the axiom, yes?
No.
But of course, if you want, you need an axiom.
Yeah.
You need an axiom that every line segment can be extended to a unique line, yes? Yeah, if you really want to see these axiomatic geometry, they are really caring about each sentence that they are writing down, okay? But anyway, what should I do then?
If I remember correctly,
Yeah.
you draw a parallel line that crosses A.
Okay, am I using an axiom to do this?
Yes.
And that's the parallel axiom, because how should I know there exists such a line, and if that line exists, why it is unique? But I say that I draw the line that passes through A and parallel to this BC. Yes? Oh, I hope that this looks parallel, okay? Yes, but why? So you see, I am using the parallel axiom to be able to do that, and then I want to use this corresponding or the consequences coming of this theorem. I don't know which one is which. Might be we do not use the axiom. We use an immediate consequence of the axiom. So if I want to write it, so let me call it, for example, let me call it L. By the way, I can write BC, but of course, if I want to be very careful, I have to write this BC like this. But I will not be very strict in these kinds of rules. So I would say that I myself drew this L parallel to BC, so I can write L parallel to BC. And let me use this for and. And then you need to give me the role of transversal. So you need to tell the reader, the audience, that which one of them you are going to take as a transversal. So let me write AB is a transversal. Yes. And then what is the consequence of this? So you see, if you want, I can extend it to view it better. You really don't need to do that. So I'm telling you that this one is parallel to this one and this one is a transversal. So this Z shape is a good thing to remember, yes? If you have a real Z, these two angles should be the same. It's not the axiom, but it's an immediate consequence of the axiom. And of course you can have letter N as well, or something like that. Okay, they are the same. So you see my Z shape, it can be also the other way around, inverted Z, yes? Or inverted, and so that's easy to understand. So these two are parallel, this is transversal, so this angle, which I call it A1, is definitely equal to this angle B. That is not the axiom, but that is the immediate consequence of my axiom. And now what I do, I would write L is still parallel to BC as before, but now I change the role of the transversal and give it to AC. AC is a transversal. And then what happens, what can I conclude? The Z shape appears here, do you agree? Then it means that what I call A sub 2, for example, is equal to this BC. Is equal to C. So A2 is equal to C. And then now arithmetics comes in. You see, so here we do not have any geometry involved. This was geometry. I concluded that. Then I'm adding. This is a number. This is a number, by the way. This is not the angle itself. So I add these, and I add A to it. This becomes A plus B plus C. Yes, by A, it's a little bit sloppy notation. By A, I mean this. Okay, so this is exactly what I want to discover, but this is, if you look at this, you see that this is the whole angle, which is 180 degrees. This angle is 180 degrees. And I want you to pay attention. If I change the triangle, I don't change the names. Especially consider special cases. So I have this A, this B again, this C, this A, this B, this C. Yes? You need to convince yourself that if I change the shape but keeping the names correspondingly the same, it doesn't matter which type of triangle, which size I am using, this will be exactly the same. I don't need to change even one single slightly thing. I can do the same thing. So this means that in this case, I have shown that this relation is true for every triangle. Yes? And then we considered something else. Do you remember? We had some notion. Today I repeat a little bit, but from next time I will not repeat anything at all. I just try to teach you new things. So I have a triangle ABC. If I extend a side from one of these directions, I make an angle here. This is called an exterior angle. Exterior. Yes. So we can say this is an exterior angle corresponding to vertex C, because I can do the same thing for A and B. The reason that I don't say the exterior angle corresponding to C is what? Yes?
There's another one.
Because there is another one, yes? Because I can, instead of extending this one, I can extend that one. But then this is also another exterior angle, again corresponding to the same vertex C. But the point is that the measure, this is the word that we use for the size of an angle. The measure of this angle and that angle are always the same because they are opposite angles, yes? So if I care only about the size, I can always consider one of them. And this is the standard way that people use usually. For example, if you have ABC, and then what I have, if I extend that one from this, this is usually you extend this one and consider this, and then you consider this one. This is the way that people usually, if they want to draw all three of them, this is actually a nicer way to do it. So this is an exterior angle corresponding to vertex C, an exterior angle corresponding to vertex A, and the same for B. Okay, there is nothing that much if I want to explore the relation between an exterior angle and the interior angle corresponding to that. That is very clear, yes? So what is happening? If I have this angle, C1, let me call it, and this one, C2, of course it's very clear that C1 plus C2 is always 180. So it means C1 and C2 are what we call supplementary angles. So C1 and C2 are supplementary angles, so that is more or less very obvious. But we have also a better relation, yes? That I really want you to know it in this way. Of course, you always can explore things from scratch, but when you want to prepare yourself for problem solving, you really have to be quick. So try to know all of these things by heart. And that was the theorem we discussed the previous one. Do you remember? By the way, there is a name for it. So you see, this is called the interior angle adjacent to this exterior angle. But there are two other internal angles. These are called opposite interior angles corresponding to that exterior angle. So I don't know. You can also probably use non-adjacent interior angles, but this is the terminology I have seen in many books. So they call it opposite interior angles. And then what I want to show, and actually we showed before, I want to remember this by heart, and then I will give you today some examples so that we can solve them. So here, what we have here, if this angle, let me call it alpha, and then let me call this interior angle beta, and this interior angle gamma. So you see, beta and gamma are interior angles opposite to this exterior angle. There is a very nice relation. So alpha is beta plus gamma. Yes? So I want you to know it in that way. But why is that true? It's very clear. So let me call this one theta. We proved that alpha plus beta plus gamma is 180 because these are the This is the sum of the interior angles of a triangle. And we also know that alpha plus theta is also 180. So this means that these two should be the same. And then I cancel alpha, so beta plus gamma is theta. And that is, did I make a mistake?
No, I think you mixed alpha and theta.
Yes, where?
Alpha
Alpha
should
and
be there.
theta is 180, that is correct.
Yeah, but it should be theta plus beta plus gamma should be.
Ah, here.
No.
No, that's correct.
One under.
This one,
That one.
that one.
No, not that one.
Let me discover it myself. Ah, okay, this one. That one is theta. Beta plus gamma plus theta, yes. So this is theta, and that is probably, theta is cancelled now. Yeah, thank you very much. So theta is cancelled, what is left is plus alpha. Yes. Is that right now?
Mhm. Right.
So yeah, remember this by heart. But before giving you some kind of examples, this session would be probably a lot of examples. But before that, I want you to understand there is a very nice consequence of this regarding to this this theorem. So here the axiom was this: if L1 and L2 are parallel, and a third line cuts both of them, the corresponding angles are the same. Now, the converse, by the way, we don't call it inverse. If you have P, if P, then Q, assume that P is a statement. A statement is a declarative sentence, which is either true or false. So if I assume that I have two statements, and then one of them implies the other one, meaning that if this is true, the other one is also true. This is called an implication. This is a statement in its own right. It's a compound statement. I have P and Q, simple statements. I combine them with this arrow, and I read it if P then Q. It means that if P is true, then Q is true. If I interchange the role of Q and P, this is also another implication, but this one is called the converse. I don't know, this is the word that they use, it is the terminology. The converse of the previous one. So if you interchange P and Q, that is called the converse of the previous implication. And then, I don't know, I have told you even in my lessons that even if this one is true, there is no guarantee that this one is true. They are completely independent implications. For example, if I want to give a simple example, as I usually do, if x is equal to 2, everyone agrees that x squared is also equal to 4. If I ask you, is this implication true or false? You will say it's true. But assume that I am working on the set of real numbers, and I imply this. For example, I say that if x squared is 4, it implies that x is equal to 2. This one was true, but this is false. Because there is no guarantee. If, of course, you are working on the set of natural numbers, yes, that is also true. But if I am working on the set of real numbers, if x squared is 4, there is no guarantee that x is definitely 2. It might be minus 2. So you see that this, I have interchanged the role of these two. So this is called the premise. And that is the conclusion. Yes? So here, if I interchange the role of the premise and the conclusion of an implication, I get another implication. That implication is called the converse of the previous implication. And there is no guarantee, even if the implication itself is true, there is no guarantee its converse is true. This is very important in geometry, because many times we want to understand if the other way around is also true. Yes, for example, in the realm of geometry, if I can say, if I have a triangle whose two sides are equal, then the angles opposite to those sides are equal. The converse is that, what is the converse? If I have the triangle whose two angles are equal, then the opposite sides are also equal in size. Which, of course, in this case, is it true or false?
Yes. True.
It is true, yes? And if both of them are, so let me just give you another example. So if x is equal to 2, then I can conclude that x to the 3 is 8. This is true. What about the other one? What is the converse? The converse assumes that this is the case, implies that this is the case. Is it true or false?
True.
This is also true, yes? So you see that I gave you a very simple example. Implication was true, its converse was false. The implication is true, the converse is true as well. And these are very, very important statements in mathematics. When you want to summarize both of them, because both of them are true, you use this arrow with the double sides, and then you write x to the power of 3 to the 8. And there is another way to say this. We say equivalent. So what does it mean? It means mathematically, x equals to 2 and x to the 3 equals to 8 are the same. Not the same, they are not identical, but they are completely equivalent. And that is probably one of the beauty of mathematics. Which one is easier for our brain to understand? X equals to 2 or x is 3 to the power 3 to the 8? Definitely x equals to 2 is easier for us to understand. And that is the mission of mathematics. To explore simpler probably statements that are equivalent to the harder statements. So this one, whatever this can do in mathematics for you, this will do the same thing. But which one will serve the job better probably for our brain? This one. Okay, and then there is another one, we call it if and only if, because here we say that if x equals to 2, then x to the 3 is 8. Here we say that if x to the 3 is 8, then x equals to 2. But because both of them are true, we say that x equals to 2. We don't say if. We say x equals to 2 if and only if. And then this sometimes the abbreviated writing IFF. Okay, now let us go back here and discuss about somehow the converse of this theorem. Do you think the converse of that theorem is true? Do I need another axiom for the converse, or I can deduce it from theorems? So let us see. So do you understand the point? The point here is this. I have two lines which I don't know yet if they are parallel or not. We don't know that. But we know that there is a third line, let us call it L, which intersects with both of them, and we know that this angle and this angle are the same. So you see, I am changing the role of the premise and the conclusion. In the main theorem, I know L1 and L2 are parallel. The axiom claims that alpha and beta are the same. Not claims, asserts that alpha and beta are the same. But here, I know that alpha and beta are the same. My question is that, can I conclude that L1 and L2 are parallel? That's also important, very important to understand. Simple but important. What do you say now? Intuitively first. Do you think intuitively this is right?
Yes.
It seems right. But now logically, or if you want to conclude, do you think I need another axiom to add to the set of my axioms, or I can conclude this from what you see on the board? One powerful tool in geometry, especially in proofs for geometry, is proof by contradiction. Yes? It's a very, very powerful tool in all areas in mathematics, especially in planar geometry. So you see, this is your assumption. You assume that this is true. Someone actually measured these angles, 100% precise. And then they claim that, of course, 100% precise is not possible physically, but assume that. Alpha is equal to beta, and then we want to conclude that L1 is equal to L2. Let us see what happens if this is not the case. This is the proof by contradiction. So we say that let me write it in this way. This is the standard way of writing if you want to write it, because you need to learn how to write as well. So assume that my claim is that L1 is parallel to L2. Assume that this is not the case. And L1 is not parallel to L2. Let us explore the consequences of such an assumption. So what is the consequence? Yeah, you need to imagine. So assume that these two lines are not parallel. So what happens if they are not parallel? So if they are not parallel, it means that when I continue them, I'm trying to actually, what happens? So for example, because if they are not parallel, it means that they will intersect at a point, yes? If this is not going to happen, they have to intersect at a point. And this gives a contradiction. This cannot happen if you insist to keep this assumption and then meanwhile violate this. Because if you violate this, you have to admit something like this is going to happen. But this is in contradiction with the assumption that you are insisting on. Why is that? Yes?
Because alpha has to be beta plus that other angle.
That other angle, yes? Because you see now, if this is going to be happen, what is the name of this shape? A, B, and this point, for example, C. What is the name of this shape that you see here? Because I have these are not curves, by the way. They are straight lines, yes? So this is a straight line, that's a straight line, and because that's the continuation of these two, and that is just a straight line. So this ABC is a triangle. If this is a triangle, can I call it an exterior angle?
Yes.
That is an exterior angle. So this exterior angle, according to what we had, which we concluded from the axiom itself, by the way. So somehow I am using the axiom to prove the converse of the axiom. I want you to understand this logically. So alpha is beta plus whatever you want to call this angle, I don't know, theta. Yes? But then what happens, this cannot happen because you are telling me that alpha and beta are equal. So on the one hand, I have to admit alpha and beta are equal. On the other hand, based on this logical system that we set up so far, I have to admit this one. But these two cannot happen at simultaneous. Or, for example, you can say that theta becomes 0 if alpha and beta are the same. And this cannot happen because if they intersect, this theta cannot be equal to 0. Yes? So you see now, this is important. So whenever, I want you to understand that this is different, completely different. If I guarantee you that these two angles are the same, if you want to, you can immediately conclude that these lines involved are definitely parallel. And it doesn't matter if they are corresponding angles. For example, what happens if I give you this angle alpha and this angle beta? If I give you alpha and beta are equal, can I still conclude that the lines are parallel? Yes or no?
Yes.
Yes, because if alpha is equal to this beta, beta itself is equal to gamma because they are vertical, and now I have alpha and gamma are the same, and if alpha and gamma are the same, then I can conclude that they are parallel. What about this one? If I give you two lines like that, and I give you this is alpha and this is beta, and I tell you alpha and beta are supplementary, can I still conclude that these two lines definitely are parallel?
Yes.
Again, yes. Why? Because if alpha and beta are supplementary, I mean that the sum is 180 degrees. Yes? And let me write gamma. I know that gamma and alpha they are also supplementary. So comparing them, immediately you realize gamma and beta are the same. And if gamma and beta are the same, I will have the same theorem. Yes? So this is, I want you to have it in mind. Many times in Olympiad questions, you have to prove two lines are parallel. One of the strong tools in your hand should be thinking about that. Of course, we will have a lot of theorems that will come and help us in this, and that becomes it hard because then you have a diversity of theorems. One of them is applicable, one of them is not applicable, and then you have trained yourself so much that you can immediately find the best one. Okay, that fits to the problem. But that I want you to know. That is extremely important. So let me see what I'm supposed to talk about today. Because, yeah. Let me first give you some very simple ones. If I give you this scenario, if I give you an angle, and I give you another angle, for example, like that. Of course, this is so obvious that you might think that doesn't need proof. But anything except axioms in geometry needs a proof. So I put an arrow here and here. This is, by the way, standard. Instead of explaining so many things in words, when I put an arrow here and an arrow here, I mean that they are parallel. Yes? And when I put, for example, 2 arrows here and 2 arrows here, I mean that these two are parallel. Okay? So instead of explaining in English, I just write that. Intuitively, what do you think about these angles?
They're the same.
They are the same. But why? So from now on, we cannot say that this is clear. No. The only ones that we agreed upon are the axioms. So why this is true? Yes?
Well, I don't. This might be a overcomplicated method, but I mean, I guess if you could extend
this one,
that one, so it
from this,
so it intersects.
Yeah, exactly.
And then we find that.
So now tell me exactly how many times you want to use this theorem. I think 2 times. Yes. So you see, you say that this line and that line are parallel. This plays the role of the transversal. So if this is beta, I can call this one beta. Yes? And now this line and that line are parallel. This will play the role of the transversal. So if this is beta, this is also beta. So this means that they are the same. Is that understandable? It was trivial, but you cannot say it is trivial or this doesn't need proof. You need to tell me. So, and then you see that it was not trivial because actually I used a theorem 2 times, even not once. Is that clear? So everything in geometry needs proof. So do you think this will affect the situation if I cross the lines? For example, if I have this and this. But I hope that this, of course, I want you to rely many times on your intuitions. I don't want to kill the intuition here. But I mean that intuition is a good guide to see what to do, and then we have to go to prove it. Do you think that I can claim still alpha and beta are the same?
Yes.
Yes? Yeah, but why?
Because their transfers will by the same. Like,
yeah, but this one, I really don't need to add this line. So I would consider, if you want to be very precise, if they write it in words, for example, if they say that if the arms of angles are correspondingly parallel, prove that the angles are the same, this is not enough to consider only this one. Because this one and this one more or less needs different procedures for the proof. If I want to write this, I have to start with this word that I extend this arm. But I don't need to extend any arm there, yes? So in principle, I'm just telling you the logic, but these are so simple. So this is automatically equal to that, and this one is equal to this. This means that they are equal. But can you imagine that the arms of 2 angles are parallel pairwise, but they are not equal?
Well, what do you mean? Like,
I have 2 angles.
Right.
The arms of one angle are correspondingly parallel to the arms of the other angle, but still they are not equal. Is that possible? And if possible, how we can imagine that?
Like, are both the arms are parallel to the other arm?
Yes. Is that possible? I just want asking these simple questions because I want to extend your intuition.
We could say that if you draw one set of arms or one angle.
So let us consider that one. So I have one angle.
Mm-hmm.
And my question is that, can you draw another angle for me so that one arm of that angle is parallel to this, the other arm of that angle is parallel to this, and the size of that angle is not equal to the size of this angle? Is that possible?
Yes.
Yes. Can you help me just to draw it? You don't need to explain.
Just I don't know how we would just flip the arms.
Yes,
around
exactly.
so that.
So what would be the connection between the angles then? If you flip the arms.
180 minus the other one.
Yes. So they are not the same. So what he is saying is that, okay, I can have this line parallel to that, but this line, this line parallel to that. Yes? But then, of course, intuitively, it is clear that if this is alpha and beta, at least on this poor picture, you see that they are not equal. But there is a nice connection between these two. What is that? Alpha and beta are supplementary. Why is that? Can you prove for me that exactly on this picture? That's a very bad one, so let me just clean this and make it seems plausible at least. So why alpha and beta are supplementary? Yes?
If you extend the line
Here?
No, on B.
On B, yeah? Extend from this direction?
No, extend so it's.
Oh, okay, from this direction.
I mean, yeah.
Okay, so let me just extend that.
And then you can find that. Well, like it.
Yes, we can get this angle.
Yes.
If this is alpha, this is also alpha.
Yes.
And then I told you that if this is alpha, that they are supplementary. Yes. So it is easy to convince yourself. I mean that I want you to know these two ideas. So if these are parallel. Okay, but now let me consider another scenario that is nice. By the way, let me ask you one question. Can I say that if I have two lines perpendicular to one single line, the lines themselves are parallel? Intuitively first. So I have one line. I have two lines. So this is L, this is L1, this is L2. I know that L1 is perpendicular to L, that's the symbol that I use, and I know that L1 is perpendicular, L2 is perpendicular to L, and then I want to conclude, if possible, that L1 and L2 are indeed parallel. Do you agree with me here or no?
Yes.
If yes, why?
Yes.
So why?
Can we use theorems to?
Yes, we have to use theorems
Okay.
or axioms.
Yeah. So by the previous theorem that.
Which is the converse one. Yes.
So if two angles are the same, they have to be
Parallel.
parallel.
Yeah, so that's a special case of the previous one. So you see, I have two lines perpendicular to one single line. This angle and that angle are corresponding angles. If two corresponding angles are equal, then the lines are parallel, not by the axiom, by the converse of the axiom, which was a theorem and a consequence of the axiom itself. Okay, so that is also, I remember. So you see that now, you see where we are actually standing. Okay, now let me ask you another. So here I wanted to explore what are the possibilities if I have parallel arms of two angles. What happens if I have perpendicular arms of angles? So I have an angle, I have another angle. The arms of one is perpendicular correspondingly to the arms of the other one. What are the different scenarios that we can explore here? These are, by the way, these are your anchors. You have to have them. And whenever, if you need, you can use it. But of course, if you really want to use this in a competition, you really don't need to prove it. I don't think this is so trivial, okay? But I want you to understand what is going on, okay? Think a little bit about that. How many scenarios in principle we can consider. Because we have to be careful. If you want to say that something is always true, we have to convince ourselves in geometry that we are considering more or less all possibilities. Otherwise, we cannot claim something very general.
So the connection between two angles.
Yeah, so for example, I don't know, if you want, I can draw. Of course, when I draw it, this becomes very simple, yes? So if I have this, and I don't want to draw it, draw another angle whose arms are, one of them is perpendicular to this and one of them is perpendicular to this, and explore that the relation with the what?
That angle is supplementary to the first angle.
Be careful about, is this the only scenario?
No.
Yeah, that I want you to explore a little bit. What are different scenarios? I can momentarily pause recording. Okay, what happened? Let me draw one of them here for you. I don't know which one you started with. I would probably start with this scenario, okay? Okay, so if this is alpha and this is beta, what is the relation between alpha and beta?
They're equal.
They are equal in this case, yes? Is that clear? Why is that? So you say that, let me call this angle gamma. If this is gamma, what is the measure of this one? That's gamma because they are vertical. And then if I ask you what is beta plus gamma, what is beta plus gamma?
It's 90.
It's 90 because 90 plus beta plus gamma should be 180. This is 90. And then you also have this. Gamma plus alpha is also 90 degrees. One of them in this right angle triangle, the other one in this right angle triangle. So then I hope that you agree with me that alpha and beta have to be the same, yes? Okay. Is this the only scenario?
No.
Yes. And so what is the other scenario?
Well, if you draw.
The vertex is outside. Now we can keep the vertex inside. Yes. So what do we say? So we have this, for example, and then I have the vertex of the second angle inside the angle, the first one, and I draw this line perpendicular to that, and this line perpendicular to this. Yes. And then this angle alpha, this angle is beta. Of course, even intuitively they are not equal, but it is clear what is that, alpha plus beta?
They're supplementary.
They are supplementary. Why is that?
Because it's a...
This shape is a quadrilateral. It consists of 4 sides. And then what was the sum of the interior angles?
360.
360 degrees. And that is, this is already 90, this is already 90. So alpha plus beta plus 90 plus 90 is supposed to be 360 degrees. So the share here will be 180. That's also... But of course, you should be a little bit more careful. If I put this completely here, do you think this will affect the result? So I mean that at least you need to think about it and convince yourself. For example, if this is alpha, I can have the vertex here. I have to extend this, by the way, to draw this vertical line. And then, for example, I can draw this line. Okay, hopefully... Why do you think? Are they the same or not, by the way?
They're the same.
If this is beta, do you claim that alpha and beta are the same? So why is that?
It's when proving these geometric things, can't we just assume that we can always transport these lines around without, like I said, parallel transport them?
Yes, but you have to convince yourself. So you are so that is correct, because we proved that if we parallel transport an angle, the size will remain the same.
Mm-hmm.
But parallel transport is, of course, yeah. So in principle, that's translation. And if I have a rigid object and I translate it, the geometry of that shape is not changed. Even if I rotate that, So this
Yeah.
will not change. These kinds of transformations are called isometric transformations, so they are not affecting the sizes.
So shouldn't we then be able to translate this beta, the sides for beta, to be the exact same case as before?
Yeah, mainly yes. But let me tell you, I think so, because, for example, we can prove that if I give you any triangle, you can do a transformation called an affine transformation and transform that triangle into an equilateral triangle. And of course, proving theorems for equilateral triangles are simpler. But in competitions, I don't think they will buy this solution from you. Say that, okay, this has been proven that there is a transformation that transforms any triangle into an equilateral triangle. And then I can do I can go there and prove everything there and come back here. Yes?
Mm-hmm.
This makes the problem very, very simple, and I don't think they will accept these kinds of solutions. So, of course, these are so trivial they will not face them, but technically what you're saying is right. Okay, you can also think about that yourself. That is actually very simple. But I want you to understand, if we have the parallelness between the arms of an angle, we have a connection between the sizes of the angles, and if this case. By the way, let me also ask you a question in this scenario. What is the angle between the angle bisectors of this scenario? So for example, I have this angle, whatever it is. I have another angle. Here. Yes? This one is perpendicular to that one. And let me just don't draw unnecessary things. So I have this one. Now what I do, I draw the angle bisector. I draw the angle bisector of this. What is the angle bisector? It's a ray, half line, so that it divides the angle into two equal angles. And then I do the same thing for here. And I put a question mark here. What is this angle? So if I want to solve a problem like that myself, I try to put letters that I know. For example, I know that these two are the same, so let me put something A and A here to make it clear for my eyes. And then this is B and B. But do I really need to put B and B, or can I put A and A?
We shouldn't put A and A.
Yeah, you can put A and A, yes, because we just proved that the whole angle here should be equal in size with the angle. So don't try to write a lot of letters. So as soon as, if you have a relation, use it. So I will put A and A here. Okay, now can you tell me what this angle is?
Intuitively, I think it's 90 degrees.
Okay, so it means that my drawing is good. But yes, that's correct. But why? Wait, let me pause recording. Any ideas? Okay, let me tell you something, because I want to go a little bit forward, otherwise we'll not be able to finalize everything. So when I want to solve this problem, I break the problem into I look at the problem in a different way. My goal is to show, because now you have a guess for this. So try to use your intuition. You are supposed to show that this is 90. How can I prove that? Let me call this gamma. My goal is to show this angle is 90, but completely equivalently, I can show alpha plus A plus gamma is 90. Is right? If I can show A plus gamma is 90, then I am done. Is that understandable?
Yeah.
But then it is easy now, isn't it? Why? Can you just tell me why A and gamma? Because you see, I am concentrating on this triangle. If I can show A plus gamma is 90, what share will be left for this is 90.
Yeah.
How can I convince myself A plus gamma is 90? It's already convinced, yes? Because if this is gamma, what is this one?
Gamma.
It's gamma.
Oh.
But this one is a right angle triangle, so gamma plus I is exactly 890. Because I have this assumption, this is 90. So you see what I'm saying, that I changed the way that I looked at the problem. I say that, okay, instead of proving this 90, you had a guess for it, so use it. Instead of showing that this is 90, what can I do it equivalently? If I succeed to show that this angle plus that angle is 90, I am done. But this angle is equal to that angle, so I can call it gamma as well. And then I see that in this triangle, which I know is a right angle triangle because of the assumption, gamma plus A is 90 and I am done. Is that right? Yes or no?
Yes.
So you need to think in this a little bit active way. Okay, let me also, I don't know how many of you thought about this problem, but let me just do this one today. So, yeah, I draw a star shape randomly. So I don't want to be very careful in how I draw. So I have to be careful to make it straight, but it doesn't make it straight anyway. Yes, here, something like that. But all of these are supposed to be straight lines. A, yeah, B, C, D, and E. I'm not careful in the length and in inclination of these lines, but I want to keep it a star at the end, or a star-shaped object at the end. So, and I want to determine if there is something that I can say about the sum of the angles at the vertices. A, B, C, D plus E. I hope that you agree that they cannot ask you about the size of one angle, because I can immediately change the way that I draw it, and I will affect the sizes of these ones individually. But I want to see that any way that I draw it, as long as I keep it, as far as I keep it a star, then there is a number for the question which is fixed, and it doesn't depend on how I draw it. Okay, do you have the answer?
Yes.
What's the answer?
180 degrees.
Yes, that's very surprising, yes, in the beginning. So it doesn't matter how you draw it, the sum of these angles is always 180 degrees. Wait, do you have any reason for that?
Yes.
Okay, how do you want to do that?
Okay, so the shape in the center is a pentagon.
Yes.
So the sum of the angles of that is 540 degrees.
So let me just review something a little bit. So you know that if you have a pentagon,
yes,
any kind of pentagon, so with 5, 1, 2, 3, 4, and then 5 sides, yes?
Yes.
So I can divide it into 3 triangles. The size of the internal angles for this is 180, the same here is 180, the same here, yes? 180, so then we add them, it becomes 540. And then we also had a formula, because in competition it's really important to have a strong memory. So if I have an n-gon instead of pentagon, n sides, then do you remember what was the sum of internal?
N minus 1, 180.
No, not n minus
2.
N minus 2, and it is easy. How many sides you have here? 5. How many triangles you were able to get it? 3. And you can convince yourself the number of triangles that I can make is 2 less than the number of sides, and each triangle has 180 degrees. So this is important to remember, or at least immediately be able to detect it correctly, to recalculate it correctly. So that is the sum of the interior angles of an n-gon. Yes? Okay. So then So what you are looking at, you say that this is a pentagon. Now I agree with you. So and then you know the sum of these angles is 180 times 5 minus 2, which becomes 540. Yes.
And then I considered the sum of all of these 360-degree angles and like in the intersections of the
Okay.
pentagon.
So I don't understand what you mean. So the angles that you considered are these angles.
Yeah, so I thought about like the total sum of all of them together, which if you have 5 360-degree angles, like the sum of all those angles is 1,800 or whatever.
The sum of each one of these.
Yes,
You
of
mean?
each one of those.
Okay. So you are this if I call it alpha, beta, gamma, theta, and lambda,
Yes.
you know that alpha plus beta up to lambda is 540. And then what you are saying is that if I go around that, it is 360 degrees. That's
Yes.
what you say.
Yeah.
And the same thing here, the same thing here, the same thing. Okay, then.
So and then I also know the sum of the angles of the opposite angles.
Yes.
So and that's also for 540, and so I have the sum of those angles, the pentagons, sum of the angles, and the opposite angles sum, and then I have the rest. I have if I subtract that from 1,800, I have the sum of the angles of the.
Yeah,
of
I
those.
think it's correct.
Yes.
It's correct. What about others? Did you? So you were absent that time, but did you find a way?
Mm-hmm.
Yes. So do you want to more or less do the same thing or no? Okay, let me keep the name at least for the time being. So the way that you did it was correct, I think. I didn't follow exactly the detailed calculations, but the idea was correct. Okay, then.
Yes, we have said that. Oh yeah. Then we can say that.
No, let me first ask you this question. Was it completely different from Oscar's logic? That's more or less the same thing. Might be some differences. But there is a very simple way to do that.
Mm-hmm.
I want you to think a little bit about that. What you did is correct, of course. And I want to, do you remember the experience? Sometimes this idea does not work if you just want to do this randomly. Do you remember I gave you a problem? Then just adding the angles and working for finding that triangle. Do you remember?
Mm.
Yeah, that is usually what. Okay, but I think there is a very simple way to do it, which doesn't involve any kind of pentagons. Or I think so. So let me clean them. And that is the notion. I told you that is very important. It's very trivial, not trivial, obvious, but that is the notion of the exterior angle. So what can I do here? Look, instead of calling these angles, let me call this one alpha. Okay, but this alpha, let me ask you, I want you to train your eyes to catch these patterns. Alpha is an interior angle for this narrow triangle on top, of course, but it is an exterior angle for a triangle. Can you read it? Can you tell me what that triangle is? If you want, I can give the names of these so that you can name them. So let me write M, N, P, Q,
It's
R.
MBD.
MBD. Do you agree? Alpha is an exterior angle to this triangle. Is it true or false? It's true. Why? Because I have just extended this arm. So alpha is equal to the sum of the opposite interior angles. So B plus D. Agree or not?
Yes.
Okay, then continue. What do you think I will do? Because be careful, what I am interested in is the sum of these. It's hopeful because at least I have the sum of two of them right now. Yes?
So the sum of exterior angles is always 180. So if you just keep doing that, will you find 180? Is that what you're going to do?
Oh, that was not my intention, but that's probably also working. But I want to try to look at this angle now. Yes, beta.
Yes.
Beta is also an exterior angle for one triangle that you see. What the triangle is?
EMC.
What?
EMC.
Yes, this triangle. NEC. You see? Yes, so then beta is what? Is the sum of these two opposite interior angles. Finished, isn't it? Beta is C plus E. But what I am asking is the sum of them, so it motivates me to add them. So then this becomes alpha plus beta is equal to B plus C plus D plus E. Agree or not?
Yes.
But in this sum, one is absent, is A. So add A. Then we are done. Because I know this. Yes? What is this one? These are now interior angles of a triangle. This narrow one. So this is 180. Isn't it simpler?
That's
Because the first intuition, I started doing the pentagons. But the way that I did it was a little bit different. I actually constructed another pentagon. And then I want to try to see if I can. I was able to do it in that way as well. So I want to find these. Because you see that when I am catching these things, it is easy to get rid of them. Because at the end, when I consider all these, this bigger pentagon and the smaller pentagon, then I will at the end, I will concentrate on the sum of these angles. Then in each one of these triangles, I can use that. But I think this is the simplest possible way. I think I was able to get it. Is it clear?
Yeah.
Okay, so you see, this idea is extremely powerful, and it might not be trivial. That the point of this exercise is to teach yourself exactly at this moment that I need to broaden the way that I look at the geometric shapes. Yes, because it might. If I wrote this, it was not easy why I write this alpha. But you see, if you extend the way that you look at the problem, then you see immediately this becomes an exterior angle to this triangle. Then you might use this. Is that right? I don't know. I want to give you probably. I were able to find some of them in different books, but let me tell you. I'm not saying that this is always working, but at least this is the way that you need to train yourself for. But let me draw another shape and ask you something question. I don't know. This is just also a random shape, more or less A to B, and then I go to C, then I go to D, E, F, and I go back to G, and then here. I don't know. So let me just name them. So A, B, C, D, E, F, and G. Okay? Again, I want to find the sum of all angles in these vertices. A, B, C, D, E, F, and G. Okay? So let us see what you say at this time. Here. I will pause the recording a little bit so that I can give you time to think a little bit. So you saw that I just tried to make it similar to my drawing. I mean that I didn't put this inside here. So I just respected the relative positions of these points with respect to each other, not the exact length and angles. I think because there are 5 minutes left, if you don't mind, let me add 2 more shapes with the same question mark. And I want you to explore that. The way that you mentioned it, Rasmus, I was thinking that what happens if we have just broken this and we have one intermediate point. Do you think the result will change if I have 2 intermediate points? 3 intermediate points.
Yeah, I think
That's also a good problem to think. Always in mathematics, try to generalize things if possible. So here, more or less, this is the star, but then instead of having these 2 lines intersecting at one point, then I have split it into 2 lines. But what will happen if I have more lines involved? 3, 4, and 5, okay? Think also about that, but then I want to add 2 more pictures. That would be a good idea if you think about these problems. So the problems that we will face becomes harder in nature, but we also need to have the theory. I want to extend the way that your information regarding different theorems as well. But the one that I have here is something like that. I have A to B, B to C, C to D, D to E, E to F, F to, oops. I want it to pass through. Might be this is not the best picture, but I mean there is a triangle here. You can draw it in different ways so that A, B, C, D, and then I have E, and then I have F, then I have G. So draw it in a way, of course you can think in different options. So draw it in a way that you can see at least a triangle here. Yes, and I want to answer the same question. Okay? And then one more, I can draw it like this. So I want to answer the same question for these 3 different shapes. The only thing that I messed up a little bit is this is so narrow, and I think it's essential to have that. And you also think about what happens if I have more intermediate points. Is it possible, from the idea that I got from you that this is a star, a little bit deviated, let us deviate more with putting more points here? Do you think this will affect the result? Of course, if I put more points, then I will have more vertices. What do you think? Do you think if I add them, somehow the answer will remain the same, or it will affect the result? Let us explore these, okay?
Yeah, I think maybe, I mean, I tried on a star with only 1 added, and it increased by 180 degrees.
Each time, you mean?
I think it does.
Okay, so that's good to explore these things and try to convince yourself that this is indeed happening. Yes, I think we end here, and then next time probably I will mix this with problems and theorems, hopefully. But yeah, you need to be patient a little bit from these simple things to pass from them and then explore more interesting things. Thank you very much. From now on I will upload the videos on YouTube. The previous one was not probably that very organized, so I didn't want to put it on YouTube. But from now on, I will put the videos on YouTube. Thank you.